I'm going to use this problem to illustrate how it's useful to look at the area under graphs. Here's our problem. Starting from rest, you accelerate at 5 meters per second squared for 3 seconds, and then at 4 meters per second squared for the following 4 seconds. What is your velocity after these 7 seconds? Well, the first thing I think of when I see acceleration and time, and you want to know velocity, I know that those 3 variables are related by this equation. And we can rewrite this equation, manipulate the variables a little bit to write it in terms of change in velocity. And if we wanted to, we could just find the average acceleration and plug in 7 seconds for time. But it's not going to be really easy to find the average acceleration. We know it's somewhere between 5 and 4, probably close to 4.5. But we accelerated at 4 meters per second squared just for a little bit longer than we did at 5. So it's going to be somewhere a little bit less than 4.5. And I'm just going to classify this a pain in the butt to find what the average acceleration is. So let's take a different approach. Let's find the change in velocity over the first 3 seconds and then add that to the change in velocity over the next 4 seconds. Our change in velocity for the first 3 seconds would be the acceleration during those first 3 seconds, average acceleration times that time interval, plus the average acceleration for the final 4 seconds times that slightly longer time interval. And I'll give little subscripts here just to distinguish that these are different A's and T's. But we know what they are. Here's what they are. The 5 meters per second squared, and the first time interval was 3 seconds. And to get our overall change in velocity, we add that to the acceleration for the final 4 seconds times that 4-second time interval. And we do some math. That's 15 plus 16 equals 31 meters per second. But here is where it gets interesting. This is the point I was trying to get to, where we make a graph of the acceleration versus the time. So up here on the y-axis we have acceleration in the units of meters per second squared, and on the x-axis we have time in the units of seconds. Okay, so let's graph out our journey here. Our acceleration was at a constant 5 meters per second squared for 3 seconds, and then very suddenly it dropped down to 4 meters per second squared acceleration. And we had that as our constant acceleration for the next 4 seconds from that period at second 3 to second 7, and then we just kind of stopped. That was the end of the story. And if you look at this graph, it's kind of 2 big rectangles. There's one on the left and one on the right here. And if we were to, well, let's find the area of these rectangles. We know that the area of a rectangle is the height times the width. So here the height is 5. This A means area. Area is height times width. 5 times 3 is 15. And the area of this rectangle is its height times its width. It is 4 high, and it is 4 wide. 16. These numbers should be looking familiar. When we add up the areas of both these rectangles, we get 15 plus 16 equals 31, which is exactly the change in velocity that we saw in these exact same circumstances. So hopefully what I've convinced you is that if you look at the area under a graph of acceleration versus time, that area will be equal to the change in velocity. So I'm going to go ahead and conclude that the area under this graph equals change in velocity, which was 31 meters per second. And look, if you're not convinced yet, remember here was our 15 for the first 3 seconds for our change in velocity. Here was our 16 for the next 4 seconds. We added them together, got 31. And compare that to the areas of these two rectangles. And this is a really handy thing to remember if you have a graph where it's hard to break it into specific sections. And in this case, you'd have to use calculus, which is another video for the 241 students. But that's only half the story. We're looking here at finding velocity from acceleration and time, but you can do this with all sorts of other variables that are related. For instance, we can do the same kind of trick to find displacement, delta x, if we know average velocity and time elapsed. So here we've got another situation where we have an unknown variable equals one thing times another thing. And the one thing is going to go on the y-axis, and the other thing is going to go on the x-axis. And so here, if we graph the velocity versus time, and say we have a situation where the velocity increases until say 5 seconds, we can figure out the displacement of this object over that 5-second interval by looking at the area under the velocity versus time graph. Let's look at a kind of simple situation where your velocity in meters per second is 30 meters per second, and you just keep going 30 meters per second without changing your velocity for, I don't know, 10 seconds. And you're asked, okay, how far did you travel over those 10 seconds? Well, how far did you travel is just asking your displacement over those 10 seconds. So we know that if we're just given a graph like this, we could just find the area under that graph. And this is just a rectangle. One side is 30, another side is 10. So we can do the area equals the displacement equals 300 meters. Wait. I'm setting a bad example. Always use units. 30 meters per second times 10 seconds. We can see the seconds cancel. We get seconds over seconds, which leaves meters as our unit, and our number is 30 times 10, 300. And in this simple case, looking at the area under the graph isn't any different than just using the equation. Here, delta x equals the velocity, the average velocity here is the same as the constant velocity. If a velocity is constant, or anything is constant, its average is just that same number. And the time was 10 seconds, so it's really just the same thing. And looking at a graph can also tell you, if we're looking at this velocity versus time graph, we can also figure out the acceleration at any point by looking at the slope of the graph. And we can see that at any point, the graph is perfectly flat. It is not sloped at all. It has a slope of 0. So there is no acceleration at any point here. And we know that anyway because, we were told this is a constant velocity of 30 meters per second. If the velocity is not changing, there can't be acceleration. But just for laughs and giggles, here's what we would do to find the acceleration at, say, a point 5 seconds on the velocity versus time graph. If we wanted to find instantaneous acceleration here, we would find the slope of the tangent line to the curve. The curve here isn't really a curve, it's just a straight line going across. And the tangent line that goes through this point would be exactly on top of the graph. So technically we would find the slope of that tangent line to the graph at that point, which again is a slope of 0. It's completely flat. So the acceleration at that point, or at any other point on this graph, is 0 because the slope is 0. But here's a more interesting scenario. Maybe in this case, our velocity increases steeply at the beginning and then kind of doesn't increase as fast toward the end. And we are asked the question, what is the instantaneous acceleration at the time exactly 2 seconds? So to do that, we find the point on the curve that represents the time 2 seconds. So here's 2 seconds on our time axis. So we just follow that straight up. We find this point on the graph. That's the point that's going to tell us everything about the instantaneous acceleration at time 2 seconds. What we do is we write a tangent line through that graph, or through the point on the graph there. So this line should only go through that one point on the graph and no other points. And the slope of that tangent line should be the acceleration. And here's a little refresher for how to find the slope of a line. The slope is the rise over the run. What we can do is just look at some particular segment of this tangent line. I'm going to look at this segment here. And the delta y is this length, which looks to be about 1.5. And the delta x, the change in x over that segment of the line, is exactly 2. And just to clarify, why did I do 2 minus 0.5 equals 1.5 here? Well, this is essentially the change in y, which is y2 minus y1. So here the y value was 2, and down here the y value was 0.5. So our slope is that that change in y, which we just saw is 1.5, over the change in x, which is 2. So the acceleration at time 2 equals 1.5 over 2, which is 0.75. And since we've been consistently using SI units, it's safe to assume that our answer is also in SI units. So it's meters per second squared. And then we could look at another point in time, maybe up here around 7 seconds. We can follow the graph up, see that it's flattened out. So here, if we draw the tangent line through that curve, it's going to be mostly flat. So the slope is going to be just about 0, which tells us that the acceleration at this time is pretty much 0. So it's pretty much done accelerating. Even though it's going faster, we get higher on this curve, which means a higher velocity, but we're just kind of done getting faster. So A is almost, somewhere around 0, maybe a little bit above 0. But that is only half the story about looking at the slopes of tangent lines on curves. So here we found acceleration by finding the slope of the tangent line to the velocity versus time graph. But we can also find instantaneous velocity if we look at a position versus time graph. So I just changed what the y-axis is. I changed it from velocity to position. That changes entirely what this graph means. So now the instantaneous, the slope of the tangent line at any point on this graph gives us the instantaneous velocity. So I'm going to go change all our A's to V's. And now we can think about what the slope here means if the position is changing. If the position is changing more rapidly, that means a higher velocity, and the higher the slope, that means the faster the position is changing. Looking at this point up here, the position isn't changing very fast at all, which means the velocity is very low, probably near zero here. Again, the velocity here is the slope of this tangent line to the curve.
Made with Doodlecast Pro.